next thing I wanted to talk about with you is a buffer solution. This is a concept you should have seen in class already, so can you tell me what is a buffer?
Buffer solution, is it? I don't know, actually.
Okay, so let's talk about that. So there's two key things to understand about a buffer solution. A buffer solution contains both a weak acid and its conjugate base. And the other key thing about a buffer is that a buffer resists changes in pH. It's harder to change the pH of a buffer than of a normal solution. It's harder to change the pH of a buffer than of a normal solution. All right. All right, so we've been going over the different cases of how to calculate pH. We've seen each of them is a little bit different. The way you find the pH in a buffer solution is you use the Henderson-Hasselbach equation. Okay, so let's figure out what would be a good form for the Henderson-Hasselbach equation. So do you see, remember a buffer consists of a weak acid and its conjugate base. Well, remember that in general, a good way to draw a weak acid, what's the definition of an acid?
Something that donates protons.
Good.
And accepts electrons.
Good. So generally we draw a weak acid in general like this to show that it has a proton to donate. And then how would we draw its conjugate base?
Separate the proton and the acid molecule.
Yeah, so how if we draw the weak acid as HA, what would be a good formula for its conjugate base?
HA minus.
Could you repeat that?
Right, A minus.
Yes, it's lost the proton, so it's just an A minus now. So notice that the Henderson-Hasselbach equation depends on the amount of acid and the amount of its conjugate base. So let's try to figure out what would be the right form of the equation here. Should we put the acid on top or the conjugate base on the top? Well, let's say that we increase the amount of the base. If we increase the amount of the base, would you expect that to increase or decrease the pH?
Decrease.
Any particular reason?
Because if you have a high conjugate base, then that means there's going to be a high conjugate, or not a high conjugate, but a high concentration of protons.
Why?
Because,
oh, okay. I see. Because you said it was produced from the acid. All right. Now, when we're making a buffer solution, the way you make a buffer solution is that you just add a bunch of the acid and you add a bunch of its conjugate base. They're not being produced from each other. These are just the initial amounts. We're adding a bunch of the acid and a bunch of its conjugate. So you're not necessarily going to have a lot of protons because the A minus isn't being produced in solution. We're just adding it separately. So the equation does look like this. But the A minus that we're adding didn't come from the acid. We just added it separately. We just took a bottle that was full of the acid and we poured it in, and we took a bottle of the conjugate base and we poured it in. So they're not coming from this equation. Well, the way to think about this is this an acid or a base?
It's a base.
If you add a lot of base, is that going to make the solution acidic or basic?
Basic.
Would that increase or decrease the pH?
Increase.
So it looks like our first way of looking at that was incorrect. Adding a lot of base should make the solution more basic. So does the amount of base move in the same or the opposite direction as the pH?
Same direction.
How about if you added a bunch of acid? If you add a bunch of acid, would that increase or decrease the pH?
That would decrease the pH.
Because the more acid there is, the more acidic the solution should be. So does the amount of acid move in the same or the opposite direction as the pH?
Opposite directions.
So which of these two forms would be correct? So notice that we want the amount of base to move in the same direction as pH. So here's the pH on the left side of the equation, and here's these ratios on the right side of the equation. Which of these fractions would show that the amount of base moves in the same direction as the pH? In order to get the amount of base to move in the same direction as the pH mathematically, do we want to put the base on the top of the fraction or the bottom of the fraction to influence the pH?
Top of the fraction.
So it looks like we're looking at this version. And then remember, the amount of acid should move in the opposite direction as pH. So do we want to put the amount of acid on the top or the bottom of the fraction to have the right effect on pH?
Bottom.
Okay, so I just wanted to explain a little bit of the basic intuition behind the Henderson-Hasselbach equation. We won't prove the equation, but this part of the equation should make sense.
So the first one that I wrote down was wrong?
What I was trying to do was I wrote down the Henderson-Hasselbach equation, but I didn't say which way the fraction was. I wrote it with an or because I wanted us to figure out which way is correct. So now we can see the correct way is to put the base on the top and the acid on the bottom. The correct way. So what we wrote down before wasn't finished because I wrote it with an or. I wrote it two different ways. And now we've seen the correct way to write it. The correct way to write it is with the base on the top and the acid on the bottom. This just shows that the more base you add, the more basic the solution, so the higher the pH. And the more acid you add, that'll make the fraction smaller, and that'll give us a lower pH. So if you forgot whether the base went on top or bottom, that's something that we should be able to figure out from this equation. In any case, we should just memorize this is the Henderson-Hasselbach equation. This is what's used to analyze buffer solutions. If you have a combination of a weak acid and its conjugate base, you use the Henderson-Hasselbach equation to find the pH. Okay. Tell me when you have this problem written down.
Okay.
Okay. Do you have that acid-base handout we've been working with in the past?
Yeah.
Okay. Do you have that in front of you?
1 second. Yes.
So remember, that shows that there's many different types of problems. So if you can see at the top of that handout, maybe I'll pull it up myself here. There's a bunch of different types of problems. There's problems where you start with pure water. There's problems where you start with a strong acid. There's problems where you start with a strong base. There's problems where you start with a weak acid or a weak base. We haven't covered all of these. There's problems where you could start with a weak acid and its conjugate base. Which of those categories does this problem fall into? Take another look at the problem. Which of those categories is this?
Weak acid.
Okay, that's not correct. That's not correct because we do have a weak acid, but that's not all that we have.
And a weak conjugate base.
Okay, that might not seem like a big deal, but that's a totally different type of problem. A type of problem where you just have a weak acid is solved completely differently than when you have a weak acid and its conjugate base. That's the tricky thing about, that's why it's taking us some time to go through this acid-base material, because every problem is solved a little bit differently. So the point of the handout is to remind us that each of these types of problems is solved a little bit differently. So the types that we've gone over is we've gone over how to solve problems with pure water. We've gone over how to solve problems with a strong acid. We've gone over how to solve problems with a strong base. We've gone over how to solve problems with a weak acid. We haven't done the weak base, but hopefully you won't be tested on that. And lastly, I wanted to go over this case. This is another case your instructor went over in lecture, an acid and its conjugate. The reason these are all separate is because they all have slightly different methods. So this is what we could call a buffer, right? How can we recognize that this is a buffer?
Yes.
How would we recognize that? What is a buffer?
Oh, sorry, I didn't hear you. Because we have the conjugate base and an acid.
We have both the acid and its conjugate. So these problems are solved completely differently than the ones we did before. Do you remember all the previous problems? We wrote the chemical equation and we did a before change after table. Now you could use that approach here as well. You could use that chemical equation and a before change after table here as well, but there's a shortcut for these problems. For buffer solutions, there's a shortcut. All we have to do is plug into the Henderson-Hasselbach equation. So for buffer solutions, we can just use the Henderson-Hasselbach equation. You can only use the Henderson-Hasselbach equation for a buffer. You can only use this, this is only for a buffer. Only for a buffer, we can use the Henderson-Hasselbach equation when there's both the weak acid and its conjugate. So what is the Henderson-Hasselbach equation? What's the general equation?
pH is equal to pKa plus the log of A of the conjugate acid over, or the conjugate base over the acid.
So let's try plugging into that. What should we plug in for pH? Well, I won't plug in anything for that because that's what the question is asking us for. We can make a note that that's what the question is asking us for. Now this problem asked us for the pKa. Did the problem tell us the pKa directly?
No.
But it gave us something we could use. How could we figure out the pKa here?
Get the negative log of 1.74 times 10 to the negative fifth.
Okay, good. That was kind of a trick question. A lot of students would say that this number is the pKa. But remember, we don't want to confuse levels. Ka is at the concentration level. pKa is at the P level. So this problem, we have to find the pKa. So go ahead and do that calculation and tell me what you get.
I get 4.759.
And I'll round that to 4.76. We were working on this problem, so refresh your memory of the problem. Here's the problem that I'd given you. Now, remember, there's a bunch of different types of acid-base problems. They're all solved a little bit differently, so we need to remind ourselves which type is this. So again, from the acid-base handout, which of the types of problems is this problem?
This is a weak acid and conjugate base problem.
Yeah, acid and its conjugate base. And what we're learning is that's solved completely differently than if you just have a weak acid by itself. Do you remember last time we saw if you have a weak acid by itself, you set up a chemical equation, you do the before change after table, and then you use the Ka to solve it mathematically. But here, with a buffer solution, there's a shortcut. All we have to do is plug into the Henderson-Hasselbach equation. The Henderson-Hasselbach equation only works if you have both the acid and its conjugate. So remember, we need the pKa, so we were figuring that out. So what should I plug in here for the pKa?
For the pKa, plug in 4.76.
Not the Ka. We don't plug in the Ka, we plug in the pKa. We have to know what level we're working at. What do you think I should write here?
.04 over 0.08.
Okay, now what?
Calculate.
Yeah, all right, so tell me what you get.
Get 4.458.
Round that more carefully.
Is it 4.459?
Yeah, because the next digit is a 9. So, okay, now what?
Now we're done.
Yeah, we have to know when we're done, because what does this represent?
pH.
Okay, as you can see from the equation. Okay, so that's how to do this type. I think this will be just about the last type of acid-base problem that you and I will work on, and then we'll move on to something else. So the key thing is notice this was solved again completely differently from the other acid-base problems that we did. So to review, what type of problem is this again?
Acid and conjugate base problem.
So I'll label that acid plus conjugate base. Problem. And the key thing is to see this is solved completely differently than the other types of problems. You can only use the Henderson-Hasselbach equation when you have both the weak acid and its conjugate base. The other types above this on the handout we solved differently. So when we cut out, I was reminding you that this type of problem is solved differently than the other types that we went over before. People have difficulty with this material because it's hard to keep track of the different types of problems. So remember, strong acid, strong base, weak base, those types of problems are not solved with the Henderson-Hasselbach equation. The only situation where you can use the Henderson-Hasselbach equation is the weak acid and its conjugate. So you might want to make a note of that here in this handout. There wasn't room in the handout for me to write down how to do each method, but you might write this is the case where we use the Henderson-Hasselbach equation. Notice you don't want to plug in the Ka. You have to plug in the pKa into this equation. Okay, so you'll need to memorize this Henderson-Hasselbach equation. So please stare at the Henderson-Hasselbach equation until you feel you have it memorized.
Okay.
Okay. Notice who goes on top, the conjugate base or the acid?
The conjugate base.
That's important that's a common source of mistakes, putting the wrong number on the top or the bottom of the fraction. So that's something to be careful about. Notice pH is on the left and pKa is on the right. We don't want to confuse those either. Okay, so without looking at your notes from memory, what is the Henderson-Hasselbach equation?
It is pH is equal to pKa plus the log of the conjugate base over the acid.
The log of the concentration of the base over the concentration of the acid. Okay? When can we apply this equation?
You apply it to buffers.
And what's a buffer?
It's an acid with its conjugate base.
Good. Notice that if you didn't have both of those, you'd have to put a 0 on the top or the bottom of this fraction. And that wouldn't work. You can't divide by 0, and you can't take the log of 0, as we talked about before. Okay. And also to review, do you remember what's the other key feature of buffers? What's the kind of the purpose of a buffer?
A buffer is something that resists the change in pH.
That's important. Yeah, that's what I was going for. Okay.
Is that a capital M or a lowercase m? For the top.
Capital M. Okay, well, let's try this problem on your screen.
It's 0.866.
What's the next digit after the 6?
I can't. Oh.
Well, what was the next digit after the 6?
I can't read it.
You're using your cell phone again?
Yeah, it doesn't show me.
Okay. I definitely would recommend using the same calculator you're going to actually use on the test. So that's a good thing to carry around with you so you can practice on that same type of calculator. Okay. So if you can't see the next digit, you can't tell how to round it off. Okay. In any case, that's the correct answer. What do the brackets mean in your second equation?
The concentration of...
Point.
Oh, I don't need them there, though.
Notice it doesn't really make sense to put those in. There's no such thing as the concentration of 5 times 10 to the negative 4. That doesn't mean anything. I think we talked about how that's a common student mistake. You put the name of a species in brackets, but it's meaningless to put a number in the brackets here. Okay. Remember on these problems that it's important to be careful to put the right number on the top and the correct number on the bottom of the fraction. Here we did that correctly. Okay. All right, so which type of problem was this from the handout?
This was a weak acid and conjugate base problem.
Right. How would you attack this problem?
Is it 1 over 5.7?
That's right. So ratio of x to y, how would you turn this 5.7 into a fraction?
5.7 over 1.
Now the ratio of y to x should be the reciprocal of that. What would you do next?
I don't know.
It might seem like a weird question, but this is not a really simplified answer. Next, you would use your calculator to figure out what this is. So let's use our calculator to do that.
.175.
So let's figure this out. How did you get that?
1 over 0.1 is 10.
Okay. Or you could say the ratio is 10 to 1. Tell me when you have this written down.
Okay.
Now, do you see this is another problem about a buffer? Because we're going to have both the protonated and the deprotonated forms of acetic acid. So what's the key equation to use?
The key equation is the Henderson-Hasselbach equation.
So what does that equation say?
pH is equal to pKa plus the log of the concentration of the conjugate base over the concentration of the acid.
Now, what's this question asking us for? What would be a good way to write what the question is asking us for mathematically?
What is the ratio of x to y?
What would be better symbols for x and y here?
What is the ratio of A to HA? Or A minus to HA?
Like this?
No, the other way around.
So it's very important to put the correct thing on the top and the correct thing on the bottom. Here the question mentioned protonated first, so we'd want to write the ratio like this. So this is a common type of question. Let's see how to solve this. What would I plug in here for the pH?
For the pH, 4.76.
What would I plug in for the pKa?
4.76.
Now, in this type of problem, I'm not going to plug in anything for A minus and HA because this is what the question's asking us for. Can you see any way to start simplifying this equation?
Could you cancel out the 4.76 on both sides?
What would that leave you as the new equation?
0 is equal to log base of the concentration of the conjugate base and over the acid.
How did you do that cancellation?
Subtract 4.76.
That's right, from both sides. Now what? How could we rewrite this equation now without the logarithm?
Without the logarithm, I don't know.
Well, remember that we did a lot of exercises on how to rewrite equations without logarithms?
Oh, yes. You do 10 to the power of 0 is equal to A minus over HA.
How could you simplify the left-hand side?
This is 1 is equal to A minus over HA.
So, what's the answer to the question? Here was the question. What's the answer to this question?
1.
Because 1 over 1 is 1. So this is how to solve this last type of question here. This can be the last type of question we do for these types of acid-base problems. Oftentimes, we're given both the pH and the pKa, and we have to find the ratio of the protonated to deprotonated forms. How would you turn this into a fraction?
1 over 1.
What does it mean if the ratio is 1 over 1? What does that mean in common sense terms?
It's equal.
Who's equal?
HA and A.
Yeah, it means that we have equal amounts of the acid and its conjugate base. So what have we learned here? When the pH is equal to the pKa, you always have equal amounts of the acid and its conjugate base. The Henderson-Hasselbach equation tells us that when the pH is equal to the pKa, you always have equal amounts of the acid in its conjugate base. I'm sorry, were you saying something?
I was going to say the exact same thing.
Okay, good. Now remember, what's the difference between pH and pKa? What does the pH tell you about, and what's the pKa tell you about?
The pH is the negative log of the concentration of protons, and pKa is the negative log of the Ka.
Okay, that's good. But what does that mean in more common sense terms? What's the difference between the meaning of pH and the meaning of pKa? This is something we talked about in our last session.
pH is just the acidity. Is measuring acidity.
So how's that different from pKa?
I don't remember.
Okay, that's a good thing for us to talk about again. So remember in our last session we said that actually there's two different types of acidity. There's the acidity of the solution and there's the acidity of the molecule. Remember we made a little chart and we said there was the acidity of the solution and there's the acidity of the molecule. pH, does pH tell you how acidic the solution is or how acidic the molecule is?
The molecule.
How would you work that out? How do you calculate pH?
Is the negative log of the concentration of protons.
And the pKa? How do you calculate that?
Is the negative log of Ka.
So which of those is based on a property of the molecule and which is based on a property of the solution?
Molecule is pH and pKa is the solution.
No, I guess we're not understanding that. The Ka is the equilibrium constant of the acid. The Ka is the equilibrium constant of the acid. It's a property of the acid, a property of the molecule. But H plus tells you how many protons there are in the solution. The H plus is not directly related to the molecule. H plus means the concentration of protons in the solution. So the pH measures the acidity of the solution. pKa measures the acidity of the acid, because the Ka is a property of the acid. So those are important things to keep in mind. It's important not to confuse these two concepts, because we're going to keep using these. Okay, so what's the basic difference between pH and pKa? What does the pH measure in words, and what does the pKa measure in words?
The pH tells you the concentration of protons in the solution, and the pKa measures the acidity of the acid.
Okay, so one measures the acidity of the solution, the other measures the acidity of the acid. So what happens when you put, say, HA in a solution? Or what happens when you have a combination of HA and A minus? Well, the HA could give protons to the solution, or the solution could give protons to the A minus to turn it into HA. So suppose we have a situation where the pH is lower than the pKa. In this case, who's more acidic, the solution or the molecule?
The solution, the molecule.
Like this?
Yes.
How did you come up with that?
Because pKa measures the acidity of the acid, and pH measures the acidity of the solution.
Right. So is the pKa here big or small?
Big.
And does that mean the molecule is highly acidic or not very acidic?
Highly acidic.
I think you might have forgotten that from the last session.
Oh, it's highly basic.
Yeah, this is where it's really helpful if you can do the homework problems. I don't expect anyone to remember everything from the sessions if they don't practice it. So it's important that we start getting into a rhythm where you're able to do those problems each time. Okay, so anyway, do you remember last time we did a whole big exercise about how Ka and pKa go in opposite directions? And even aside from doing the homework, it's important for you to review the tutoring notes between each pair of sessions. So it's important for you to review the sessions, review your notes and review the sessions, if necessary, review the video on your own so we don't have to review those together too much. Okay, but if you remember last time we talked about how there's a big difference between Ka and pKa. So to review, if the pKa is big, does that mean the molecule is acidic, or does that mean we have a relatively strong or a relatively weak acid?
It means we have a relatively weak acid.
Right. Remember, that's because the pKa is the negative log of the Ka. So the bigger the pKa is, the smaller the Ka is. They move in opposite directions. Okay, so suppose we have a situation where the pH is less than the pKa. Who's more acidic, the solution or the molecule?
Say that again.
If we have this situation where the pH is less than the pKa, who's going to be more acidic, the solution or the molecule?
The solution.
Which is the opposite of what we guessed here at first. Because a low pH means highly acidic solution. Solution's more acidic. So what's going to be more favored? Are we going to expect the solution to give protons to the molecule, or the molecule to give protons to the solution?
Solution gives molecules to the solution. The solution gives molecules.
Repeat that one more time more clearly, please.
What were the choices?
The question is, do we expect the solution to be mainly giving protons to the molecule, or do we expect the molecule to be giving protons to the solution?
The solution is giving protons to the molecule.
So which of these two forms of the molecule are going to be favored? Are we going to have more HA or more A minus?
We're going to have more HA.
Because it's getting protons from the solution. So we see here, when the pH is less than the pKa, is the acid mainly in the acidic form or the conjugate base form? Is the acid going to be mainly protonated or deprotonated?
Protonated.
Right. Now, if the pH is bigger than the pKa, does that mean the solution is, who's more acidic, the solution or the molecule?
The molecule.
So, do we expect the acid to be mainly in the what do we expect to be favored? Do we expect the solution to give lots of protons to the acid, or do we expect the acid to give lots of protons to the solution?
The acid gives lots of protons to the solution.
So which form of the acid will be favored, protonated or deprotonated?
Deprotonated.
That's right. Why? Because the molecule is so acidic, it's going to give up most of its protons. Here, the molecule is so acidic, it's going to give up most of its protons. Do you see how this is the opposite outcome than when the pH is less than the pKa? So the point here is that when you put the molecule in a solution with a very low pH, the molecule tends to be largely protonated because the solution is so acidic. But when you put the molecule in a solution with a high pH, the molecule tends to be deprotonated because it's giving protons to the solution.
Hold on, let me write that down.
Okay, so these two examples are important.
So, to recap, when the molecule is placed in a high pH solution, the molecule gives protons to the solution. But if the molecule if the solution is more acidic than the molecule, then the solution is going to give protons to the molecule.
That's right. Yes, that's correct. So that is these two cases. So it's important to know these cases, and you should be able to figure it out if you forget it. So the way that, this might not be the way your instructor explains it, but this is the easiest way for me to figure this out. You can suppose that when you're comparing the pH and the pKa, you're comparing who's more acidic, the solution or the molecule. And that tells you whether the solution will mainly be giving protons to the molecule or the molecule will mainly giving protons to the solution. And that tells you whether the molecule will mainly end up in its protonated or its deprotonated form. And that turns out to be a very important issue in biochemistry. By the way, why is this so important? Why is it important to know which form is going to be more important? Well, do you remember when we were going over organic chemistry, do you remember I kept repeating, what did we say was the most important factor? What did we say was the most important factor in organic chemistry?
Charges.
So that's also the most important factor in biochemistry. Biochemistry, the most important factor is the charges. So do you see why it matters which of these forms predominates? Because they have two different charges. For example, in this case, the protonated form is neutral and the deprotonated form is negative. So if you have a molecule floating around in the cell, in biochemistry, if you change the pH, that has a big impact on whether it's protonated or deprotonated, and that affects its charge. And its charge affects what its shape is and how it can react. So this is very important for biochemistry because the charges have a big impact. Protonating or deprotonating changes your charge. Okay, now if the pH is less than the pKa, we have more protonated than deprotonated acid. And if the pH is bigger than the pKa, we have more deprotonated than protonated acid. So what would happen if the pH equals the pKa?
Then you have equal amounts of proton concentration.
Equal amounts of what?
Acidity in both the molecule and the solution.
That's true. That would mean that the solution and the molecule are equally acidic. But that's just a step in the thinking. Then what we care about is the molecule going to be mainly in its protonated or its deprotonated form?
It's going to be in its...
Well, if...
equilibrium.
These are all equilibriums. These are all equilibriums. But if a lower pH gives us more protonated and a higher pH gives us more deprotonated, then logically speaking, the only thing possible when the pH equals the pKa is that the amount of the protonated form equals the amount of the deprotonated form. You'll have equal amounts in both forms.
Say that again.
I'm just saying that logically speaking, if this is what happens whenever the pH is less than the pKa, and this is what happens whenever the pH is greater than the pKa, it should be logical that when their pH and the pKa are equal, then the concentration of the protonated form is going to be equal to the concentration of the deprotonated form of the acid. Another way of putting this is half of the acid will be deprotonated and half will be protonated. All right, so tell me when you have that down.
Okay.
So when the pH is lower than the pKa, more than 50% of the acid will be in the protonated form. When the pH is greater than the pKa, less than 50% of the acid will be in the protonated form. And when the pH equals the pKa, 50% of the acid will be protonated and 50% will be deprotonated. That's just another way of looking at what we said. Now, do you see that this case here is the one that we already proved using the Henderson-Hasselbach equation? Remember that here we did an example where the pH of acetic acid was 4.76. I said the pKa of acetic acid was 4.76, and the pH of the solution was also 4.76. In this example, where the pH and the pKa were both 4.76, what was the ratio of the protonated versus deprotonated forms of the acid?
1.
Could you repeat that, please?
1 to 1.
Yeah, what does that mean, 1 to 1?
That they're equal?
That means that we're equal amounts of both forms. So we could use the Henderson-Hasselbach equation to prove. You can prove from the Henderson-Hasselbach equation if this number equals this number, that gives you a 0 here. 10 to the 0 is 1, and that means you're always going to have equal amounts of both. So this part you can prove with the Henderson-Hasselbach equation. In fact, all of these parts you could prove with the Henderson-Hasselbach equation, but we'll save time and not go through all those details. Okay. Do you know what the name of this type of functional group is?
Carboxylic acid.
That's right. This has a pKa around 2. So any acid has 2 different forms. What's the other form of this acid?
The conjugate base.
Yeah, how would I draw that? What does that look like?
With a negative oxygen instead of a hydrogen.
That's right. So let's say, do you know what the pH is at physiological conditions?
7.
Yeah, to be more accurate, it's about 7.4. So in physiological conditions, carboxylic acids would take, which form would predominate? The protonated or the deprotonated form?
Say that one more time.
If we put this carboxylic acid in the body under physiological conditions, I'd like you to use the techniques we were just talking about to figure out which form of the carboxylic acid will predominate. Will we have more of the protonated form or more of the deprotonated form?
We would have more of the deprotonated form.
How did you figure that out?
Because the pH is more acidic.
So,
hold on, I didn't think this one through yet. It would be the deprotonated form, because the pH is more likely, the pH is a little bit basic, or it's more basic, and would donate protons to the acid.
try to speak more carefully. Try to use nouns rather than pronouns to say what you're talking about. Try to be specific about whether you're talking about the acid or the solution. Well, I'll help you with that. So, who's more acidic here? The molecule or the solution?
The molecule.
So is the molecule mainly going to give protons to the solution, or will the solution mainly give protons to the molecule?
The solution will give protons to the molecule.
Like this?
No, the molecule will give protons to the solution.
Like this?
Yes.
Okay. So will the molecule mainly end up protonated or deprotonated?
Protonated.
So the protonated form will be the major form?
So, no, the deprotonated one.
Okay.
Major form.
Okay, that was the answer that you gave before. So your answer before was correct. You were just having some trouble explaining your logic here. So this will be the major form in this case. Your answer was correct, but we want to go through the logic for that. So in physiological conditions, this carboxylic acid will mainly exist in the deprotonated form. So what will be the charge on the carboxylic acid? Positive, negative, or neutral?
Negative.
Mainly negative. Okay. Let's say that the pH was 5. What would be the major form then?
Still the deprotonated form.
Because the pH is still greater than the pKa. Suppose the pH, but would you agree that when the pH is 5, even though this would still be the major form, it would be less extreme?
Yes.
Because we're getting closer to equality. Remember, if the pH equals the pKa, there would be equal amounts. Suppose that the pH was 1, which would be the major form?
The protonated version.
Because now the solution is more acidic than the molecule. So the solution will give protons to the molecule. So what would be the charge of the major form?
Neutral.
So notice that the molecule would change charge if you change the pH. By lowering the pH, you can change the charge on this molecule. Okay?
So after I write this, I want to kind of explain it so it will help solidify in my mind.
Good.
I have written down, so when the pH of the molecule is not as acidic as the solution.
Well,
then
that already is kind of unclear. You can't say the pH. You would say the pH is a number. So you would say the pH is higher or lower than the pKa. And that would mean the solution is more or less acidic than the molecule. Do you see what I'm saying? You could say that you could say pH is bigger or smaller than the pKa. And from that tells you that the solution is more or less acidic than the molecule. It's important to try to speak clearly here so our thoughts are clear. It doesn't make sense to say the pH is more or less acidic. pH is a number. A number can't be acidic. You don't want to say the pH is more or less acidic. You want to say the pH is a bigger or smaller number than the pKa, and then that allows you to compare whether the solution is more or less acidic than the molecule. So here's the kind of terminology we should be using.
Okay. So if the pH is bigger than the pKa, then the solution is more acidic than the molecule.
That's actually not true.
If the pH is bigger than pKa, then the solution is less acidic than the molecule?
That's right. This is, again, something we talked about last time. Remember, if the pH is big, does that mean that the H plus is big or small?
H plus is big.
Like this?
No, because it's a negative log, so it's small.
Right. This is something we worked on last time. Remember that because P is the negative log, the P of X moves in a different direction than X. This causes a lot of confusion to people. The P of X moves in a different direction than X. So if the pH is big, is the H plus big or small?
Small.
Does that mean that the solution is acidic or not very acidic?
That means the solution is not very acidic.
Because an acidic solution is just one that has a lot of protons floating around it.
Oh, wait. pH, okay, pH measures the acidity of the solution. pKa measures the acidity of the molecule.
That's right. That's important.
So, okay, that makes more sense now. Because I was thinking the other way around.
Oh, okay. All right, all right. So maybe that was what was confusing you. Yeah. Okay, so this is all important to get clear in our mind. Remember, the pH is based on the H+, but that's a property of the solution. This tells you how many protons are floating around in the solution. The pKa is the negative log of the Ka, and the Ka is a different number for every acid. So the pKa is related to the properties of the acid. pH is related to the properties of the solution. That's also very important to keep in mind. We have to keep all of those straight because we're going to keep using those ideas in the course. So anyway, a big pH does not mean an acidic solution. It means the solution is not very acidic. And the pH tells you the acidity of the solution, not the acidity of the molecule.
Okay.
So you were trying to... Here you were trying to put into words what our reasoning was for these examples.
So the pH, since the pH is bigger than the pKa, then the solution is less acidic than the molecule.
That's right.
And so the one that is deprotonated is the most favored.
Yeah, because the molecule will be giving protons to the solution. If the molecule is more acidic than the solution, the molecule will be giving protons to the solution, and after the molecule gives a proton to the solution, it'll be left in its deprotonated form.
Okay.
Okay. Okay, so at pH of 3, so first of all, what are the two forms of HOCl? What's the other form of HOCl besides HOCl?
OCl minus, or minus OCl, rather.
Which form predominates at a pH of 7?
pH of 7?
I'm sorry, excuse me. Which form predominates at a pH of 3?
The OCl minus.
And how did you figure that out? What were the steps?
The solution is more acidic, so it's willing to donate protons to the molecule. The molecule willing to accept protons would be the OCl minus.
So is the solution donating protons to the molecule, or is the molecule donating protons to the solution?
The solution is donating protons to the molecule.
After the solution donates a proton to the molecule, what form would the molecule have?
HOCl.
Which is not what your answer was. So I think we got this wrong. We got this incorrect. So you were trying to, so you did the first two steps correct. You saw that the solution would donate protons to the molecule, but then you asked yourself what the molecule looks like before it gets the proton. But the point is, if the solution is donating protons to the molecule, then the molecule is going to end up with a lot of protons.
Mm-hmm.
So that we were misunderstanding the logic. If the solution is donating protons to the molecule ends up. You were writing down what it would look like before it took the proton. You would say, oh, you would say if it wants to take protons, it must look like this. But the question is, what does it look like after it's taken the proton here? After it's accepted the proton, it would be in this form. So we got that incorrect. This is an important chain of logic. Do you see how this is the correct answer here?
Yes.
Okay. What's the major form at a pH of 1?
It'd be the same thing.
Would there be more or less of the protonated form now?
More.
Even more, because there's a bigger, even bigger difference between pH and pKa. What's the major form here?
The deprotonated form. Okay, so by major form you mean the one that occurs most often.
So what this means is this. I mean that the concentration of the deprotonated form will be greater than the concentration of the protonated form.
Okay.
That's what I mean by the major form. There's always going to be an equilibrium between these. Because these are weak acids, there's always going to be a mix. Some of them will be protonated and some will be deprotonated. The major form is the one that you end up with more of. For example, here you might have about 99% in the OCl minus form and approximately 1% in the HOCl form. That's why we would say this is the major form.
Okay.
So what are the two forms of HF?
HF and F minus.
I would call this the protonated form and this the deprotonated. So if the pH was 6, what would be the major form of the molecule?
pKa is 3. The major form would be F minus.
And what were your logic steps there?
Because the solution is less acidic than the molecule is going to be donating protons, so the major form would be F minus.
Because after the molecule donates a proton, it'll look like this. Okay, that was the correct logic. That was correct. What's the major form here?
P is equal to A, the major form is. Same thing, but a higher concentration.
Higher concentration of F minus. Okay, good. How about here?
HF.
about here?
50-50.
That's right. We proved that using the Henderson-Hasselbach equation. We saw that when you plug in the same pKa and pH into the Henderson-Hasselbach equation, this ratio turns out to be 1:1. Do you know what the name of this type of functional group is?
It's an amine.
That's right. Do you know, are amines acids or bases in biochemistry?
Acids.
So would this gain a proton or lose a proton?
Lose a proton.
Okay, that actually turns out to be incorrect. It's theoretically possible for amines to be acids, but that's not how they behave in the body. In the body, amines behave as bases. That'll turn out to be pretty important. So this is a base. Remember, what's the definition of a base?
Something that accepts protons and donates electrons.
Notice that the reason this is a base is because of the lone pair. This lone pair gives us the potential to donate electrons. So what would be the two forms of the amine? Here's one form of the amine. How would I write the other form of the amine?
NH minus.
So did you say this was gaining or losing a proton?
Losing a proton.
Now, what did we say a moment ago about amines? Are we saying that amines are acids or bases?
Their bases, so it would be NH3 plus.
Okay, so do you see why we had to decide whether this was an acid or a base before we figured out what the other form was. So this does not lose a proton, it gains a proton. So is this the acidic or basic form?
Basic form.
So what's this called? This is the conjugate acid of the base. This would be the conjugate acid of the base. Okay, so is this the protonated or deprotonated form?
That is the deprotonated form.
And what's its charge?
Neutral.
And is this the protonated or the deprotonated form?
Protonated.
And what's its charge?
Positive.
You see how this is different from the earlier examples that we did. Here, the protonated form is positive, whereas before, with carboxylic acid, say, the protonated form was neutral. So the protonated form is neutral, but here the protonated form is positive. Different molecules behave differently. That's important to keep in mind. It turns out that the pKa for amines is approximately 9. So if the pH is 5, which would be the major form, protonated or deprotonated?
K is 9. Protonated version.
So what would be the charge?
Positive.
What was your logic there?
Because the solution is more acidic than the molecule, the solution is going to be donating protons, and when it's done donating protons, it's going to have the configuration of NH3+.
The molecule will. Remember to try to not use the word it. So the solution will give protons to the molecule. So your answer was correct. Your answer was correct. Okay. Okay. All right. Well, there's more to say about acids and bases, but we won't want to spend more time on this. Let's move on to the amino acid type material. But just to remind you again, we've gone over from this handout. You should go back into the tutoring notes and make sure you know how to do each of these types. So you should go back to the tutoring notes and find how do we find the pH of pure water, find an example where we found the pH of a strong acid, find an example where we found the pH of the strong base, find an example in your tutoring notes where we found the pH of a weak acid. This case you might cross out. I didn't see any examples of this in the lecture notes, so I skipped this. We didn't do the weak base case. And today we've been focusing on acids and their conjugates. That's when you use the Henderson-Hasselbach equations. So we won't have time to cover any of these more complicated situations down here. So we haven't covered any of the more complicated situations, but we went over 5 of the 6 cases above the solid line. Hopefully that'll be good enough.